This video we'll be having a look at constructible polygons. So a constructible polygon is a regular polygon which can be constructed using a compass and a straightedge. So constructed using a compass and straightedge. And the compass is used to draw circular arcs or entire circles. So you can use a compass to select the center of your circular arc or circle, and you can also fix a radius. And the straightedge is used to draw straight lines / line segments. And our goal is to use our compass and our straightedge to construct as many different regular polygons as we can. So the simplest regular polygon is a triangle. We've got a triangle which only has 3 sides. And it turns out it is not too difficult to use the compass and the straightedge to construct an equilateral triangle. So if you haven't seen how to construct a triangle using a compass and a straightedge already, you could have a go yourself trying to construct a triangle using a compass and a straightedge. And it involves constructing these 60-degree angles. And it's not too difficult to figure out how to construct a 60-degree angle, so you could have a go yourself at constructing equilateral triangles. Now let's move on to the next polygon, which is a square. So we have 4 90-degree angles and 4 equal sides. And it also turns out it is not too difficult to construct a square. So constructing a square using a compass and a straightedge is not too difficult either. And in order to do it, what you could do is construct a 90-degree angle first using the compass and straightedge. Then you could draw a 45-degree angle. You could create a 45-degree angle by bisecting the 90-degree angle. Then you can select a point and drop and use the compass and straightedge to drop perpendiculars down to these sides. And after you do those steps, you have successfully constructed a square using compass and a straightedge. Again, you can have a go yourself at constructing a square using a compass and a straightedge. So now we move on to a regular pentagon. And regular pentagon actually turns out to be a little bit trickier to construct, but it turns out to be possible to construct a regular pentagon using a compass and a straightedge. So we have 5 equal sides and 108-degree angles. So if you want a slightly more difficult challenge, you can attempt to use your compass and straightedge to construct a regular pentagon. So it does require a little bit more construction lines and circles and arcs in order to successfully construct a regular pentagon. Now let's move on to the hexagon. So a regular hexagon, you have equal 120-degree angles. Okay. And it actually turns out it is a little bit easier to construct a regular hexagon than a regular pentagon. That may seem surprising, and the reason is the 120-degree angles in the hexagon are easier to make than the 108-degree angles in a pentagon, in a regular pentagon. So one way to make a regular hexagon could be to construct 6 different equilateral triangles that form the hexagon. That could be one option. A slightly quicker way, you could draw a circle with a center of O and draw an equilateral triangle like this. You could draw an equilateral triangle and then extend some of these lines across to the end of the circle, and again you can construct one more 60-degree angle like this and extend the lines, and now you've got the 6 vertices to make your hexagon. So there's quite a few ways to construct a hexagon, a regular hexagon, using a compass and straightedge. But now if we move up to a regular heptagon, so regular heptagon has 7 sides. We've got a 7-sided regular heptagon, and now a regular heptagon in fact turns out to be the first polygon where it is impossible to construct using a compass and straightedge. And the important thing is, when I say impossible, remember you can't use a protractor, for example, to measure out the angle, so you have to do everything with the compass and the straightedge. And there are ways to approximately construct a regular heptagon, but it is impossible to construct it exactly. Assuming your compass and straightedge are perfectly accurate, it is impossible to construct a regular heptagon. So again, there are ways of approximating a heptagon, so getting really, really close to the correct angles, but it turns out to be impossible to construct a perfectly regular heptagon. Okay, now one thing I'll show you is, if it is possible to construct a regular n-gon, then you can construct a regular 2n-gon. So this is an interesting theorem. So if it's possible to construct a regular n-gon, then it is also possible to construct a regular 2n-gon. And the reason is, if it's possible to construct a regular n-gon, you can start by constructing that n-gon. So you could start by drawing your regular n-gon. And now what I'll do is have these angles here at the center of the circle. Now what I'll do is bisect every single angle at the center of the circle. So this can be done using a compass and a straightedge. So I can bisect every single angle here in the whole n-gon. And now I'll make some new points on the circle. And now it turns out all these new points I make, and if you combine the new points with the old points, they're all equidistant, or they're all equally spaced around the circle. So in fact, you can convert a regular n-gon into a regular 2n-gon by bisecting all the angles at the center of the circle. So it turns out, if you can construct a regular n-gon, you can construct a regular 2n-gon. And an example is the hexagon. So if you have a look at the hexagon again, another way of constructing the regular hexagon is to first take a triangle like this, and now we have the angles at the center of the circle, and now we can bisect each of these angles, and now this creates a regular hexagon. This is quite an interesting theorem. Okay, so what we can do with this theorem is we can construct a square, which we already know, But just using the fact that we can construct a square, we can keep on doubling the number 4. 8, 16, 32, so on. And all of these polygons, regular polygons, can be constructed with this many sides. And this is because of theorem that if you can construct a regular n-gon, you can construct a regular 2n-gon, so you can keep on doubling. And similarly for the triangle, again you can keep on doubling. So 3 sides, you can construct a 6-sided one, you can double it to construct a 12-sided one, and 24 sides, and so on. So all these polygons, regular polygons, can be constructed. And again, using the pentagon example, it has 5 sides. You can double it to get 10 sides. You can double again to get 20 sides, and keep on doubling, so on, so on. All these regular polygons can be constructed. Okay. So now what we could try to do is find all the polygons with an odd number of sides which can be constructed. So which polygons with an odd number of sides can be constructed? So which regular polygons with an odd number of sides can be constructed? And what we can see is if we can find a regular polygon with an odd number of sides that can be constructed, then we can keep on doubling the number of sides using what we've shown earlier. Okay, so it turns out it is impossible to construct the following polygons for the following number of sides. It's impossible to do 9, 11, 13, and it is possible to do 15, and in fact it is possible to do 17, which is a prime number, and 15 is 3 times 5. So proving, and an extra hard challenge is to try to construct a regular 17-gon, and the proof of constructability of a regular 17 polygon was found by Carl Gauss in 1796. So he proved a 17-sided regular polygon can be constructed in 1796. I believe he proved it can be constructed, but he didn't actually show how to construct it. So I believe someone actually showed how to construct it later on, but it was Carl Gauss who showed it can be constructed. Okay, so what is special about the number 17? This one special thing is number 17 is 1 more than a power of 2. And it's not just any power of 2, it's 2 to the power of 4, which itself is a power of 2. So you can write it as 2 to the 2 squared plus 1. So that's quite interesting. What else? If you have a look at number 3 and 5, 3 is equal to 1 more than the power of 2, which is 2 to the 1 plus 1. And this is equal to 2 to the 2 to the 0 plus 1. And 5 is 2 to the squared plus 1, which is the same as 2 to the 2 to the 1 plus 1. So it's an interesting pattern going on here. We have prime numbers which are of the form primes of the form 2 to the 2n plus 1. And these are special types of prime numbers which are called Fermat primes. And the mathematician Fermat, he conjectured that all numbers of the form 2 to the 2n, 2 to the 2 to the n plus 1 are prime, but it actually turns out what we have is the Fermat primes are 2 to the 2 to the 0 plus 1, which is equal to 3, 2 to the 2 to the 1 plus 1, which is equal to 5, 2 to the 2 to the 2 plus 1, which is 17, 2 to the 2 to the 3, which is plus 1, which is 257, 2 to the 2 to the 4 plus 1, which is 65537. These numbers are all Fermat primes, and there's a theorem which says all n-gons where n is a Fermat prime are constructible. It's all regular. So Carl Gauss proved the case for the 17 Fermat prime, and later on it was shown all Fermat prime regular polygons are constructible. Okay, and remember from earlier we have the doubling idea where we can multiply stuff by 2. You can keep on multiplying regular n-gons and getting 2 n-gons and so on. And it also turns out we can actually multiply these Fermat primes themselves together as well. And the more generalized theorem, the fully generalized theorem, is a regular n-gon is constructible if and only if n is equal to a power of 2 times distinct Fermat primes. So remember, the power of 2 thing over here just means the doubling idea where you can keep on doubling the number of sides. But the interesting thing over here is there must be distinct Fermat primes. So we can't have a prime number squared, for example. So for example, 3 squared equals 9, and it turns out a 9-sided polygon cannot be constructed. So you need the product of distinct Fermat primes. So an example is n equals 3 times 5 equals 15. A 15-sided regular polygon can be constructed. However, a 25-sided polygon cannot be constructed. And if you use the doubling idea, you can show, for example, 2 cubed times 3 times 17-sided polygon can be constructed because it is of the following, of this form. And going back to Fermat primes over here, it turns out that if you do 2 to the 2 to the 5 plus 1, it turns out this number is not a prime number. So Fermat's conjecture from several hundred years ago turns out to be false. And this is because this number over here is equal to 4294967297, and this is equal to 641 times 6700417. So just because of this factorization, this is not a Fermat prime, so a polygon with this number of sides cannot be constructed. And it also turns out it's currently known that the numbers from f5 to f32, so this is where fn is equal to 2 to the 2 to the n plus 1, these are all known to be composite. So all numbers from f5 to f32 have been known to be composite using computers, because these numbers get pretty large, so it's too difficult to find if they're prime or composite by hand. These numbers are known to be composite, and it is unknown if there are any more Fermat primes. So it could be possible that these are the only Fermat primes. So that's an unsolved conjecture, whether there's any more Fermat primes apart from these 5 numbers here. Okay, so you can actually say it's unknown exactly which regular polygons are constructible because we don't know what all the Fermat primes are. But what we do know is, if we do know all the distinct Fermat primes, then all the regular polygons that are constructible will be of this form. So a power of 2 times distinct Fermat primes. Okay. And also online, we can actually search up how to construct a regular 257 gon and 65537 gon. So it is too difficult to do by hand, but it is possible for a computer simulation to perform this construction. And it takes quite a lot of steps for the 257 gon and the 65537 gon. Okay, so that's all I have for this video about constructible regular polygons. Thanks for watching, and I'll see you next time.